Welcome to the session. What part does additive manufacturing have to play in space exploration? I'm your moderator, Ben Iannotta, Editor-in-Chief of Aerospace America. That's the magazine of the American Institute of Aeronautics and Astronautics, or you could just say AIAA if you prefer. I know that space as an outer space has come up in other sessions today, so now is our chance to really dive in. For the next 45 minutes, we're going to learn about the current methods and applications and also look at what we can expect in the coming years. And we'll, of course, reserve time for audience questions via the Q&A function on your screen. So now let's meet our panelists. We've got Paul Gradl. Paul's a Senior Propulsion Engineer at NASA's Marshall Space Flight Center in Huntsville, Alabama. He's Principal Investigator for several projects and leads efforts to make components for liquid rocket engines through directed energy deposition and also other processes. He works a lot with GRC COP42, a copper alloy, and also NASA HR1, an iron nickel alloy. Next, we have Advenit Makaya. Advenit is an advanced manufacturing engineer at ESA's European Space Research and Technology Center in The Hague. He leads work on in-situ resource utilization, the idea there being to turn local raw materials on the moon and Mars into infrastructure. He contributed to the first demonstration of 3D printing with simulated lunar regolith using concentrated sunlight. That's very cool. And last, but as they say, not least, we have Cole Nielsen. Cole is founder, CEO, and also CTO of Orbital Composites in Silicon Valley. Among its goals, Cole's company has one that's particularly relevant for our talk today. He aims to break the tyranny of the rocket fairing through off-Earth manufacturing. And as the company name suggests, Cole and his team are really focused on 3D printing of composite materials and parts. So now let's get to the discussion. Let's start basic and look at why AM is so attractive for space exploration. Let's touch first on functionality. And Cole, you might be a good place to start, since tell us about the tyranny of the rocket fairing that I just mentioned, what that means and how you aim to break it. And then everybody else obviously should feel free to chime in.
Oh, that's a wonderful question. So I liken the tyranny of launch, that process, to doing something that's kind of silly. So you have your Christmas tree and you decorate it very nicely. You put all the ornaments on it. You put it in the car, and then you go through a 12-minute car crash to get to grandma's house, and then you take it out and expect it to work. In order to make that happen, you have to spend about 75% or so of the satellite engineer's man hours designing the system for launch when it may operate on orbit for 20 years. 15%, maybe 20% of the engineering time goes to operations, not to launch. The fairing in itself means that you need to design things that fold up like origami, have lots of hinges, umbrella-like things, and the actual environment of launch is extremely loud. The noise will break things. It would tear paper, as an example. Or you having to build things that are very vault-like in order to survive in that environment. Not mission operations, that's just for launch. That's the tyranny of the fairing.
Okay. Let's see. So composite parts, that's kind of how you aim to break this tyranny. Can they really be as strong as metal parts?
So the thing about composites is that when they're used properly, they can give you all kinds of things that metals won't do. So if you are trying to get heat to move in all kinds of different directions evenly, metals are a fantastic choice. Same thing with stress. But if you want stress and heat to go from one location to another, directional fibers make a lot more sense. And then composites give you the ability to tailor your material response properties in a way that's extremely difficult to do with metal. So if you want to have a spring that's very flexible this way, but not that way, composites are the best choice.
Great. So AM is requiring lots of research and development up front by, Paul's organization and Advenit's, for example. But ultimately, how will it affect costs? Why are people so excited about it?
I think I'll jump in here. So I think
Great.
Before we understand the cost, we understand why we want to use additive manufacturing, and cost is certainly a huge factor in that. But I'll go out there and say we don't use additive manufacturing for everything. And there's a lot of cases where it doesn't make sense. We have a lot of great traditional manufacturing technologies, and those are going to win a lot of times in the cost trade. So we have to first ensure that we trade additive manufacturing properly. We don't want to use it just because it's the cool new kid on the block, and it's not a solve all. So use it when it makes sense. But there are cases, a lot of cases we see when it does make sense. We can see substantial cost reductions in schedule improvement because of additive manufacturing. And a lot of times we're using it in applications that are very complex, where maybe I had hundreds of parts before that were brazed together, and now I can make it as a single part or a couple parts. The other thing is, in a lot of the aerospace applications, is we don't ever use simple materials that are easy to machine. They're always really challenging materials that have to require the high dynamic load, high heat flux environments, and they're not easy to process. And a lot of times the lead time can be 6 months on some of those materials. So I work in a different area than Cole. I work much more on the metal side, where again, we're looking at very high heat fluxes, temperature swings that can be from cryogenic all the way up to elevated temperatures. And again, those materials are not easy to manufacture traditionally. So we have found additive manufacturing for a lot of those applications. And to answer your direct question, cost savings, yes. When it makes sense, it can be substantial. We've seen 50% or more cost reduction on some of these parts, and we can see lead time reductions sometimes on the order of 10x compared to traditional parts, which is a huge game changer for us in some of our applications.
Okay.
Ben, sometimes additive is much more than cost, so it can cost more than other manufacturing techniques, but it gives you something that others cannot do. We talked about the tyranny of fairing. If you manufacture in space, if you do additive manufacturing in space, all of a sudden you can build much bigger things than what you could manufacture by conventional way on Earth and launch. So bigger solar panels, which give you more power for your spacecraft platform, so more capabilities. And additive can help you do that, even if it would be more expensive. So at the end of the day, in some application, cost is not the only driver.
So in the space arena, are we beginning to see payoff from these investments, or is that still down the road? Payoffs, I should say, in terms of reduced costs and new kinds of functionality.
What we've seen, I think, in the private sector is that SpaceX originally teamed up with 3D Systems and started producing a lot of their thrusters and other systems by printing some rocket engine. I don't know exactly everything they're doing. There's another company called Siaki, and hopefully I said that right. They produce these devices that are used to print the titanium core of a carbon fiber fuel tanks. So it's everywhere in just the right way.
So it's starting to happen, but Paul, I think you were going to chime in.
Yeah, so I think we're there on it. It is being used. We're seeing a lot of our commercial space partners using additive manufacturing across their launch vehicles. We actually have a hot fire test this afternoon on SLS, our stage test, and we have some additive manufacturing parts on that. There's some future upgrades that we're doing on the RS-25 engines. We have several additive manufacturing parts on that. I think there's 28 additive manufacturing parts. So we are using it. And I think you're seeing a lot of companies that didn't exist 5 or 10 years ago and are being enabled because of additive manufacturing. Again, because the traditional manufacturing techniques, it can be very long lead time. In a startup company, it may be difficult to take on those costs. The supply chain may not be there. So additive manufacturing opens a lot of that up. On the flip side of that, there's, and I'm sure we'll talk more of this later too, but there's definitely challenges on that too. We need to use it methodically. We need to have rigor in the process. And again, just because it's the cool new technology, we want to approach the certification, the standardization of it similar to how we do any process. We have to understand it. So that could be some of the cautions in using it and the widespread use of it, but we're getting there and we're definitely using it in applications.
In space, we started, as Paul just said, very cautiously looking at what secondary structures, so brackets, things like that, where if they fail, they don't endanger the whole mission. And now we are seeing more and more primary structures being developed by additive manufacturing, more critical parts. So it shows the increasing confidence that we get in this family of processes. For example, Ariane 5 rocket has flown several times with primary structures made by additive.
Okay, so this is going to be an evolution that accelerates or steady development. What do you think the pace will be?
I think we're going to see acceleration in this. If you look at the history of additive manufacturing, there's some applications of flight parts that date back to the early 2000s, which were very few and far between, and there's very limited number of machines in the supply chain out there. Then you jump forward to 2010, and now there's 50 companies or so worldwide that have access to machines. Now you look at 2020 and there's thousands of companies. So you're seeing this rapid acceleration of access to the technology. If you look at the literature side of it, you're seeing a lot more academic institutes and industry, putting out a lot more publications and research on this. So that is all accelerating very quickly. We're not to the point where, the machine shops, everybody has a CNC machine. We're not there yet with additive manufacturing, but that could be on the horizon.
Great.
And
let's talk, sorry, Cole, yes.
And from our perspective, we think that additive manufacturing for space exploration and transport and all these things, you're going to see a step change, because if you can build things on the ground, and you're going to go through the traditional launch window, you can optimize, but you're kind of limited by the tyranny of the pairing. Whereas if you can put the printer off world, then you can reload it and reload it and reload it and make things that are bigger than the launch vehicle, many times bigger than the launch vehicle. And that's where things get interesting.
So that's a good segue, because I wanted to talk about AM on Earth versus someday, maybe soon, doing AM in space. Which methods are most appropriate for in-space AM compared to AM on Earth? Let's go to Advenit.
No, please.
So to come back to what you said, AM in space has already happened. On the International Space Station, we have printed, both NASA and ESA, polymer parts. Astronauts have used them. So we are already there. And manufacturing will not be too far off. As soon as we start getting people on a regular basis there, we'll see the first demonstrations of additive manufacturing on the lunar surface. So what type of techniques are more interesting in space? If you are talking about human space flight, for example, you want to use as little time of the astronaut as possible, and you want to have as much versatility as possible to be able to manufacture all sorts of things, including with recycled materials, waste, plastic waste, things like that. So what NASA is currently working on and what we are looking at as well is multi-material fabrication, where the same machine can process these different types of materials, metal, polymers, this is very interesting. This gives you the flexibility and the sustainability. So yeah, we are looking into that type of that.
Yeah, and to kind of jump on this one, I think you have a matrix of possibilities to pick from. You have atmosphere, no atmosphere. You have gravity or no gravity. So that's 4 things. And when you have no atmosphere, no gravity, you're out in open space. Printing on a spacecraft with metals like wire welding or something, you're going to get metal contamination all over the outside of your spacecraft. Your optics do not like that. And your antennas might be messed up. So that's one challenge. You can do things without oxygen that you wouldn't even try down here on Earth. So you could produce calcium metals, calcium parts. You would do that here. Oxygen is just too aggressive for that. But if you're thinking, you know, 0 atmosphere, 0 gravity, polymer extrusion is fantastic. It's very clean, it's tidy, it's low energy. But if you want to think long-term spacecraft missions where you need to source feedstock, metals have a tremendous advantage because you can just go pick them up. Like I'm an asteroid, just go get some of it, throw the sand in there, and now you can print with it. But the process with metals is dirty. Whereas developing polymers off world to be printed with, now you have a whole chemical factory transport problem. So it depends on what the mission profile looks like. But I think in the near term, for devices that are going to be attached to satellites that build the rest of the satellite, it's going to be mostly solid feedstocks like wires or filaments. It's going to be not powders. And then it's going to be mostly polymer based, or the initiation and shaping of the process is going to be polymer based. You can always use an oven later.
Well, it sounds, you know, logical, but just to kind of close the loop on it, what's the problem with powders?
Gravity. So if there's no gravity and the powders are just going to go everywhere, and you're going to use electrostatic attraction or something, it's not going to work very well. It's difficult.
I see.
On the moon, powder fabrication is fantastic, especially if there's no wind.
Okay. So now with the 3D printing that's been done by Made in Space aboard the International Space Station, what are the lessons from that? Do those only apply to printing in a pressurized volume like that, or do they also apply to printing in, you know, the vacuum of space or an open space, as Cole mentioned?
Yeah, go ahead.
So I think we're exploring it, right? So again, with some of this, we have to do it with rigor, methodology. So we start out with in-space manufacturing process, which is the fused filament, free form, you know, similar to like a MakerBot that we'd use here on Earth. So putting that on space station, you know, there's tremendous lessons learned, and well, how does it feed, and what are the different convections that we see on that? We didn't want to go right to a metal application on that. We start out with plastic, and then eventually we can move towards the metal, gain confidence in that, you know, let the research community understand the physics of it. 'Cause I think that's one of the things with additive manufacturing is we get some of these processes to work, and we can make parts, but we don't necessarily understand all of the detailed physics of it. In microgravity, you know, there's a huge challenge with that too, because again, your convective melt pools, your droplets, like with a MIG type process or a WAM process, you know, you're relying on gravity. So when you move over to the metal side of it, there's just a whole new set of challenges with that. And the one thing that we haven't really talked about either is we've been focusing on the process, but there's still post-processing that you have to do. Like Cole mentioned, with some of these techniques like bound metal deposition, you have to do the debinding and the sintering of that. With some of these metal parts, we're probably going to have to do some level of machining to get the interfaces that we need with other components. And that's a set of challenges too that Cole mentioned, is now I have chips. I need to make sure that I can contain those chips and I can account for all those chips. Non-destructive evaluation of these is because even though I'm making parts in space, doesn't mean that I'm going to accept a lower quality. I'm making replacement parts that are going to serve critical functions one day on these, and people's lives are going to count on those parts. So we need to make sure that we have the right quality that we do here on Earth.
Yeah, and about that last little bit on quality, this is where we spent a tremendous amount of our time developing our robotic printing platforms, is that we want to be able to build parts that are what we would call born qualified. So, where we are today is we're kind of going this industry 4.0 thing. And that means that you need to have a digital thread or a digital twin of the process of the parts that you're building. You need to record sub-millimeter and millisecond, scale data of the entire part as it's built, and potentially monitor it with the same system when it's in operation, so you can find where the failures are going to happen. That whole system has to be unified. Huge software problem. And then this is actually the evolution of terrestrial manufacturing simultaneously. If you're going to print off world and you want to know what the crystalline formation is inside your metals or plastics, that's the same problem regardless of where you are. That's the edge of technology in general. And the leading edge of that technology is then going to go off world, which is just another layer to it.
So NASA, oh, sorry, Advenit.
To close the loop on your question on what can we learn from what is being done in the ISS. The ISS, because it's a human exploration environment, has huge safety constraints. We talked about powder. You cannot let powder float close to astronauts. You have to protect them from the heat generated by the process, and also you have to use the limited power available for the various instruments. So all of this is very important for when we print outside, where we have to avoid contamination. So it's the same problematic. You have to work with limited power. It's the same problematic. So we can already learn a lot of things from the huge constraints of humans.
So Advenit, while you're here, what is ESA planning to do in this area in space and aboard the International Space Station?
So end of next year, we should be able to fly and operate the first ever metal 3D printer on the station. So that will be the first time we print metal on orbit, and that's a huge step forward. NASA is working on metal processes as well as multi-material fabrication and machining. But yeah, we are going to open the door on printing metal.
Great. So that's another good segue, because NASA and Redwire plan to demonstrate 3D printing in the vacuum of space or open space through OSAM-2, the On-Orbit Servicing, Assembly, and Manufacturing 2 flight. If that succeeds, what would it mean for your business or your research and development?
Maybe I'll jump in there on this one since it's a NASA mission. But we're certainly excited about this one, and the goal is to assemble very large structures. So the goal on this one is to do some beams that are about 33 feet from each side of a spacecraft, and that just kind of sets the stage for what is the future of in-space and manufacturing. Like Cole mentioned earlier, being able to make components and parts larger than the launch vehicles that we're launching those on today. So that offers a lot of opportunity for larger telescopes and communications and power systems, fuel depots, which just can open up exploration, building these larger structures on that. So this is really a critical step forward in understanding how we do this autonomous assembly.
So are we headed for a day where just about every satellite or spacecraft or is additively manufactured in space, maybe even from raw material mined from asteroids or the moon or Mars or wherever? Or are there kind of constraints in that?
Well, I could share a video to this effect if you would prefer. But I think so. I think that on Earth here, a lot of our economics today, our linear economics, are driven by a certain scarcity of resources. And sometimes it's a perceptual scarcity of resources in the terms of diamonds. And so you say, oh, well, there's not enough of it, so it must be expensive. But if you're an engineer, you're like, I wish I could have more of this. There were points in time with the F-35 and F-22 programs where they just bought all of the free market titanium in the world. And they ended up cutting 85% of it away, but that's not the point. So it's the scarcity of resources that really constrains the mind. And so if you think about the battery, why aren't batteries 1% the price of what they are today? You know, well, cobalt mining is a challenge. But if there's an asteroid out there that's just made out of cobalt, we could go get it, and then, or we could build the batteries off world and land them. The pollution's gone, it's over there. And then also, you know, the batteries just come down here. So the price can drop. So there are asteroids that have, you know, trillions of dollars of raw materials in a single asteroid. Very valuable. Very valuable.
So I think if you look at, you know, very few humans have actually left Earth's bounds on this. So of course, we have a handful of astronauts on the space station continuously doing research, and some of that is additive manufacturing. Like we mentioned, there's a large infrastructure that we have to build to do that. And Ben, I think your question was in regards to, you know, launch vehicles and satellites. We still have to establish a lot of that infrastructure, which is going to take launches to do that. And that's one of the reasons that we're looking at additive manufacturing, is to be able to reduce the cost of those launches, doing a lot of that fundamental research for the propulsion systems and the tank structures, and using additive manufacturing where it makes sense in those, and certifying those processes so that we can be doing launches more regularly. And that all involves reducing the cost, increasing the performance on that through the use of additive manufacturing. So there's an opportunity there, and we still have to get a lot of that infrastructure up there to put some of those wheels in motion. But like you mentioned, the OSAM mission, decreasing the cost of launches, a lot of the research that's being done between NASA and ESA on this is just setting the stage for, you know, what we'll see in decades to come.
So before we get to our questions, and I don't know if I cut someone off just then.
I was going to try to show a video to this effect of what Paul was saying. So where's it going?
Let's have Advenit. We're going to chime in, and then we can address that. Let's see do we have the ability to show a video. We can check on that while Advenit answers. How's that?
Yes. So as an extension to your question, are we going to see everything manufactured in space at some point? For some of the things we want to do in exploration, you have no choice. For example, if you take humans to Mars, it's a 6 months journey to go there. You cannot do a pit stop on the way to reload, to resupply. So you have to manufacture, recycle in space. So if only for that, we will be in a future where everything is manufactured, sourced, and recycled in space.
Okay. So
hopefully that's coming through there.
You got it. It is.
Cool. Yeah.
It is
so
for me anyway. I hope everyone else is seeing it.
So here we're going to we're showing a kilometer scale production system. It's made out of 40-foot shipping containers, but you know that's just notional. And then the question is, you know, how do you cut the transit time to Mars in half? It turns out that rockets don't scale forever. They only get so big before gravity crushes them while you're building them. Chemistry has limits. But if you could build the rockets off world with no gravity, they can get tremendously large. So as Paul pointed out, our friend from NASA, look at how many shipping containers that is. We have to launch and launch and launch and launch to get this shipyard factory up there. And then using in situ resource utilization, we can then start to find the right materials, and then, as an example in this asteroid, and then use a variety of tools to adapt to the available materials. And then once we've done that, we end up with the ability to adapt our tools to the feedstocks that are available because our environment is different. And then we can design our objects from the tools and materials that are available. And then that's really the next stage. Sort of adaptive design, because we're going to have to use, with the carbonaceous asteroid, we're going to use carbon fiber. With metallic asteroids, we're going to use metals.
Okay. So thank you for that. That was really interesting. So let's look a little bit at, since we know this kind of large scale manufacturing isn't going to come right away, and as Paul mentions, significant infrastructure has to be set up out there in space to accomplish it. Let's look a little bit about at launch again. Why is it, how do you build trust in additively manufactured parts, or are we there?
So again, looking at additive manufacturing, it's relatively new in the grand scheme of things. Like I said, there's been parts that have flown 20 years ago, but really the access to the technology has been more or less in the last 5 years for metals. And we've been very limited in the number of metals available. You have thousands of traditionally manufactured materials. With additive manufacturing, it's growing, but generally you go to a vendor or a service provider and they have a dozen materials. So there's a lot of advancements that can be made there. A lot of the launch vehicles that we're using today, were developed a couple decades ago. It's not an easy feat to go develop and certify and go into production of launch vehicles. So we're using some traditional technologies, but again, we're looking at upgrades for a lot of those and using additive manufacturing where it makes sense. And again, we'll be launching for a while to establish the infrastructure and the ferry flights to space station and putting humans into our different exploration missions, such as the moon and Mars. On that. So that infrastructure still has to be in place, and we still have a lot to learn there. Like I mentioned earlier with the certification part of this, our first priority on this is to make sure that we keep our astronauts safe. So we have to do this with proper rigor in place, and it takes time to understand the physics of the process and the materials testing, the sensitivities of the process. We want to have all that in place and that qualification methodology before we're going to apply it to a launch vehicle.
Well, I want to make sure we have time for audience questions, so I'm going to get into some of those, and maybe we can touch on this more in some of these audience questions too. So the first one is, where do we find the most application for composites in spacecraft? I guess I'm thinking that means which parts lend themselves best maybe to composites?
Well, one of the things is specific weight, which means that for the volume of material is how much does it weigh. And so I'll give you a great example in the shuttle program. Really the origins of filament winding, which I would say is an additive process. We were doing this back in the 60s. So when the shuttles launched from Florida, the East Coast, they have these solid rocket boosters, which have basically a metal casing. But when they're launching from the West Coast, they're too heavy. So the actual SRB, the solid rocket booster casing, when launched from the West Coast, was designed and built as a carbon fiber component. This was one of the earliest examples of big filament winding, composite materials. And I mean, it's primary structure. That thing goes off, you're done, right? So that's when we did it first, or at least that's what I know.
What about like satellites, for example?
When you're trying to save weight, composites make a tremendous amount of sense. Metals are reactive in a lot of different ways because of current flow and heat flow. So when you have magnetometers, you want to put those on a boom that's extremely far away from the rest of the satellite. Well, if that boom is made out of, a wild example, fiberglass, it's not going to react to a magnetic environment. So that magnetic field sensor is going to be giving you good data. Whereas if you put it on an iron pipe and you're cutting magnetic field lines, you're going to have all kinds of currents going up and down this tube. It's going to mess up your data.
Okay.
Also, heat shields. Ablative heat shields are fundamentally a composite material.
Okay. How can nanoscale materials like CNTs, carbon nanotubes, I think that means, help the additively manufacturing processes in the field of composites instead of fibers?
Good question. There's a company called Nanostitch, and they have a material where they're basically getting these very small fibers to go between the layers of the laminate in order to, so if you have your fibers going this way, they have these little tiny particulates that are binding the longitudinal fibers together. So that's an example. But then, of course, you can also dope your matrices to get to turn it into a magnet, to make it conductive, to change the rate of thermal expansion, to the rate of thermal conductivity. You can really play with the things that are not apparent to the bulk base material. And so when you have micro and nano particulates added to your matrices and fibers, what you're fundamentally trying to do is to change the properties that are normally of the bulk. And so you're going to say, oh, I want my conductivity to go up by so many. And then you would do additives in that case.
Let's see. So here's a question that gets at the quality of 3D printing in zero gravity, like aboard ISS. Can you achieve good quality, like on the ground, or do you need special systems? And if you applied normal systems, the product's going to be like cheesecake, the questioner says.
Yeah, so that goes back to your question on what we learned from what is being done in the ISS. We know that some processes like fused filament fabrication don't depend so much on gravity. The bonding between the successive layers is pretty good, and Made in Space has done, or NASA has done some comparative studies on the Made in Space printer and show that the structure and the properties of the polymers printed in space is not so different, or not different at all from the ones printed on Earth. So when you come to what we are trying to do with the regolith, we just don't know at this point. So the gravity on the moon is 1/6 of the one on Earth. And we've been trying different types of processes. We talked about the solar sintering. Some of them use binders. This will have an effect on how the successive layers stick to each other. We get help from gravity on Earth. And that we just don't know at this point what the difference is.
Yeah, and I'll add to that.
Oh,
there's
sure, Paul.
some other complementary technologies that we're evaluating, such as the advanced simulation and modeling, can really give us some answers about how different techniques are going to work in microgravity. And some of those tools didn't exist, or the processors didn't exist, so we could adequately use those 10 years ago. So we do ground simulations of these different technologies, then use some of that data and try to validate with the models and apply it in microgravity. We also do a lot of the experiments on the KC-135, the Vomit Comet, so we can get 15 seconds or 20 seconds of microgravity on that, or simulated microgravity to test out things early. So it's not like we're designing these and just putting them on space station. There's a lot of testing and development. And the goal, of course, is to make high quality material. We want zero porosity, full density on that. And like I mentioned earlier, we need to have that same certification and quality that we do on Earth, since eventually some of these will be critical spares, critical replacement parts.
And Paul, since you're on a roll, here's a question for you, directed at you. And then, of course, anybody feel free to join in. But it says, how can universities play a role in this type of research work? We cannot go to space to try printing, but I believe some work can be done on Earth. Absolutely.
We have probably hundreds of universities engaged in research on this, as well as industry. And there's a lot of collaborations between NASA and industry and academia. We want to train the next generation of explorers. We want the engineering and the science and a lot of the courses at the universities following projects that NASA and others are doing, because again, we want those people working in this space eventually. So there's a lot of opportunities there. We have different grant programs. There's a lot of public-private partnerships with universities. There's the SBIR STTR program where industry and academia would put together a proposal to NASA on that. And I think a lot of the fundamental research that we're doing are with academic partners. So they play a very heavy role in a lot of this early development.
Okay, how's Advenit?
It's the same in Europe with ESA. We have a lot of programs directed to university co-sponsorship where ESA can fund part of a PhD or a postdoctoral project. And also on the International Space Station, there are facilities, science facilities, for example, electromagnetic levitation furnace. We soon have a bioprinter on the ISS, where universities can request or generate data from experiments on the ISS and use them for their research on Earth. So space is there to serve academia.
Great. And then here's a question that switches gears. It's another one that goes to carbon nanotubes, but it's got a little different flavor than the previous question. Is it possible to have nanocomposites like carbon nanotubes, graphene sheets, carbon flakes, fullerenes, along with traditional powders?
Yeah, today there's a commercially available product where they're putting very small fibers into a peak. So I think it's called wind form. That's a great place to start.
Peak is, just if you say what that is for us.
Polyether ether ketone, thermoplastic, very high performance. It's made by like one or two companies, and that would be for a powder bed process. And then you know there's a large number of compounders or filament makers, people that for like FDM, plenty of people that will just go ahead and start dumping stuff into the back end of that. However, when you start to deal with a lot of the very high or low surface energies of these different organic molecules, getting them to mix properly is not super easy. So getting that to mix into the filaments is not basic. But yeah, there are people that specialize in doing just that. So if you have your desktop printer at home, you can get this to happen.
Okay, I want to see if I can get this next one in. Are high strength aluminum scandium alloys and metal matrix composites being looked at for additive manufacturing for launch structures?
I can take this one. The answer is yes. We're looking at all different alloys in additive manufacturing, super alloys, copper alloys, and we're looking a lot at aluminum as well. And there's certainly challenges with aluminum and traditional, traditional welding, and even more so in additive manufacturing because it's just a bunch of micro welds. So you can get cracking, porosity in there. So there are developments out there looking at different reactive additive manufacturing, where you're adding some composite structure in there to reduce some of that cracking and making it more AM friendly. And I think that's one of the advancements we're going to see as we move forward in additive manufacturing, not just aluminum, but a lot of alloys, is developing materials and alloys specifically made for additive and not just using alloys that we've been using with traditional manufacturing processes. Because if you look at traditional manufacturing processes, yeah, those alloys were developed for that process. So it's time to develop these alloys for additive manufacturing, which ties in the question earlier about universities and research on that. There's a lot of opportunities there to dig into some of that research.
So here we're about to wrap up. I think we have time for this one more, and it's a good one because I think it goes to the approach that is being applied here to additive manufacturing and the pace of the work. If we had taken the same approach to getting to the moon as we have with AM, do you believe we would have made it in time and at the time we did?
So I'll start on that one. Again, with additive manufacturing, it's not a solve-all. We want to select the appropriate appropriate manufacturing technique that makes sense from a cost perspective, a schedule perspective. Now, one advantage that additive manufacturing does help us with is we can get to prototypes a lot quicker. I can make a combustion chamber, an injector, and turbo machinery a lot quicker and have that on the test stand in months or a year, where traditionally maybe it takes several years. So we can shorten that early development leg of it. That doesn't mean that I'm going to use additive manufacturing for production. It might make sense. It might not make sense to use it for production. But yes, we can accelerate some of that development for those missions.
So to close today's session, I want to invite each of you to give us a few parting words. And Paul, I know you were just speaking, but let's start with you and then move to Advenit and Cole.
Sure. So we're very excited about additive manufacturing. It's obviously changing the way that we're doing a lot of our component development and how we design, how we manufacture, and how we test hardware. But we still need to use a methodical approach for that and apply rigor to the process and do this safely. I think we all want to see additive manufacturing successful, but we need to do that as a community and understand it and do that safely.
I see.
Yeah, I'll conclude by saying that a lot of really exciting things are happening in space and in space exploration in particular. We are seeing what the private sector is doing with we are seeing the drive to return to the moon and later on to go on to Mars. Manufacturing in space is becoming a reality. And at the center of that, you have a common family of techniques, which is additive manufacturing. So it's like the perfect storm for this type of processes to contribute to the great transformation of what space is becoming. So.
Awesome. Cole.
Yeah, and thanks for the question. So I guess I close with a call to action, or maybe a sense of mission. And our purpose really is, we look at, the silliness of taking styrofoam cup over to Mars so that the astronauts can have a garbage pile outside their little habitat. But that's actually what we're doing here. So when you think about the Mars mission, you think about, what are they going to have to do to survive? They're going to find whatever materials they can. They're going to create everything inside their habitat. And then they're going to recycle it, because that's just energetically sensible. Once we get this technology figured out, you're going to be able to build everything you need to survive. And you're going to do it without exchanging a tremendous amount of gases with the outside world. That technology will be brought back to Earth and can be used everywhere for everybody to enable us to have a lot more humans on this planet without a tremendous waste and pollution problem. So circularizing the manufacturing, the recycling technology allows us to circularize the economies here on Earth, allows our population to scale. That's our purpose. And I hope it's yours too.
Thanks, Cole. So on that note, I want to thank Paul, Advenit, and Cole. And thank the audience for the great questions. I think those really added to this discussion. And this concludes our space exploration session.
Thanks so much.